Hey guys, in this video I want to give a quick primer on porosity for those not familiar with porosity. So before we get into the definition of porosity, I want you to know that porosity has something to do with rocks. Alright, so we have three types of rocks. They are igneous rocks. We also have metamorphic rocks. And lastly, we have sedimentary rocks. Generally speaking, in the petroleum industry, we only look at porosity when we're talking about sedimentary rocks because, well, let's face it, porosity in metamorphic and igneous rocks is usually negligible. Alright, so what is porosity? Well, porosity is defined as in terms of words, it is defined as the void fraction of a rock, at least when we're talking about porosity in petroleum engineering, because we also have porosity for other fields which are defined in different ways. So to get an idea of what I mean, let's do a quick drawing. Let's say that we take a cross section of some rock. So what we did was we take a rock sample, we cut it using a flat blade, and we look at it from above directly. And mind you, we are looking at it using a microscope, and this specifically has to be a sedimentary rock. So what you will find is that there are lots of rock grains. So forgive the drawing, but these are meant to represent some of the rock grains. So we can notice that some of them are detached, some of them are connected to each other in some ways. Alright, and so these rock grains, I'm gonna briefly color them in. Alright, so this might take a little bit of time to draw, but hopefully it gets the point across. You see that there will be some spaces which are left and untouched by the rock grains. So these spaces are what we call as pores. They are the empty spaces between the grains that make up the rock. And remember, these grains only apply for sedimentary rocks for the most part, because sedimentary rocks are created from sediments, which are just particles that are broken down from either igneous or metamorphic rocks through erosion and weathering. And these grains are transported to some place, and then they are deposited, and then they undergo a process known as sedimentation, where they are packed due to overburden pressures and cemented to make sure that the grains are stuck together. Okay, so where this represents the grains and the empty spaces are the pore spaces. So given this view of a rock, and also the definition of porosity as the void fraction of a rock, we can actually write a formula. So porosity, which is defined typically using this symbol phi, is equal to the pore volume, which is the volume of the pores in a given sample, over the bulk volume. So the bulk volume is also known as the total volume, and that is the same as the pore volume plus the volume of the grains. Alright, so let me just label these real quick so that you'll remember. So this is bulk volume, which is the same as total volume, yeah, for a given sample. This is pore volume, and this is the volume of the rock grains, and also whatever is binding them together, so the cement and also the matrix. Yep, so this is like a collective term for all those. Okay, so given that it is a fraction, we know that porosity has to be between 0 and 1. Alright, so now let's dive a little bit more in depth into some properties of pores. Alright, so now let's go a little bit more in depth into pores and porosity. So I'm going to construct another diagram. So this is again another cross section of a rock. Let's say that we have something like this. So I'm going to color white for pores. So anything that's colored in white is a pore space. So we have some more grains over here, some more grains. Okay, these are all grains. There's a grain over here. This is a grain over here. Now this will be a pore. We've got some more grains over here. I'm just gonna keep coloring in some more grains. And then I'm gonna draw this. So this is a bit of an unlikely situation. The pores and grains will never really look like this in a diagram in real life. In real life. But for the purposes of education, this is a fine way to illustrate some pores and grains. Okay, so you're going to want to notice immediately that we have some pores of varying degrees. Alright, so here we have a pore that is actually totally sealed off by some grains. So we can call these as closed pores. We have some pores which are, we're not sure what's happening, but they seem to be leading off somewhere. So we can assume that all of these are interconnected or open pores. And then we have a pore that, yeah, we know that it leads off to somewhere in one direction, but it's closed off in the other direction. So we can call these as, let's go down a little bit. These are either known as dead end or cul-de-sac pores. Now, for those of you who are not familiar, cul-de-sac is, you can say it's kind of a shape. I don't really know where it came from, but it sounds like French. Typically, we have some kind of neighborhoods which are designed in this way. You have a street that comes in here. This is sort of a roundabout, and I'm going to draw some houses using green. So we'll have some houses like this, all around this ring. So this is known as a cul-de-sac neighborhood. So I guess that's sort of where the name for this cul-de-sac or dead-end pore came from. Alright, so why are we defining all of these pores? Well, when we want to talk about pores, they're important because pores are empty spaces that will hold fluids. So this is a key idea. Pores hold fluids. And in petroleum engineering, fluids can refer to three things. They are either oil, water, or gas. Now, obviously, we are interested in oil mainly, but we're also somewhat interested in gas, and we are not interested in water. So we would like to describe how pores can hold these two fluids, which are oil and gas. So we also want to know whether or not oil and gas can flow from the pores. Well, thinking logically, if we have a closed pore, can oil and gas flow to any place if it's in a closed pore? Well, the answer to that is a simple no. However, can oil and gas flow if it is stuck in a dead end or a open pore? Well, the answer is a resounding yes. So for open and dead end pores, the answer is yes, they can flow. And if you ask why, let's just use a little bit of imagination. So from here, there's nowhere for the oil to escape. From here, at least we have some path. Here we have some path. These are all open. From the cul-de-sac, it can't escape from this direction, but it can at least escape from this direction. Alright, so based on this classification of pores, based on whether or not they are able to allow fluids to flow in or out of it, we can actually come up with some additional definitions of porosity. So then, porosity will have two types. We will have an effective and non-effective. That's a very badly written effective. Okay, so effective pores are, a porosity is made up of pores that are both open or dead end. Whereas ineffective porosity is made up of closed pores. Okay, so now how can we put that into some kind of formula that can allow us to evaluate these mathematically? Let's define porosity phi sub t, which is total porosity. And the total porosity will be a sum of effective porosity and ineffective porosity. Okay, so this term over here is referring to the open and dead end pores. And this term over here is referring to our closed pores. So for the most part, that's about it. So what have we discussed? We have discussed about the types of pores, whether or not they contribute to being an effective or ineffective pore based on its ability to allow fluids to flow. We've also given some basic definitions for porosity from the bulk, volume, and pore volume. So that's it for the primer on porosity. If you like the video, please leave a like, comment, and subscribe, and click the bell icon to get notifications. Thank you so much for watching, and stay tuned for more. Bye!